Hi, and welcome to our lesson. This is from section 2.5 in your textbook, and today we're going to be looking at and learning about how to set up a proof. Okay? A proof is the accepted form of logical reasoning in geometry, so this is important to our understanding. To begin with, a proof is simply this: a logical argument that supports some claim. Every step in the argument has to be supported by facts. So this is truly a deductive reasoning skill. Before we start to actually write proofs, we need to know how to set them up. And you can see that we're going to work with a 4-step plan. And in that plan, the very first step, by the way, as we go through this introductory section, we're going to be using this statement: the diagonals of a rectangle are congruent. And that's going to be our example as we work through the stages of setting up a proof. The first step is to rephrase the given statement as a conditional. That is, we want to write it as an if-then statement. One possibility for this one would be, if a figure is a rectangle, then its diagonals are congruent. Very good. The reason that we want to get it in conditional form is because that leads us right into step 2, which is identifying the hypothesis and conclusion of that conditional. Reason being, the given information in our proof is the hypothesis. So I'm going to draw an arrow here. Hypothesis is what's given, and in our case, in our example, we have a rectangle. What we have to prove is the conclusion of that if-then statement, and that is that the diagonals are congruent. Now, the third step in the proof writing process, and some people, by the way, would say that this comes before. They would say step 2 here, but step 3 is what we're using. It says that you should draw and label a diagram that illustrates the given information. So I'm going to come out here, and what we need is a rectangle. So I'm going to draw one. I'm also going to give it a name. I'm going to call mine rectangle RECT. As I was saying, I kind of like sometimes to have the drawing first. That's because I could refer to, in my given here, rectangle RECT, I could call it by name. And that would also allow me, instead of saying diagonals, to say that this segment TE is congruent to this one CR. So I'm going to put that out here as well. If I have the drawing first, then it makes it a little bit easier to set up the hypothesis and conclusion. Alright, and this fourth step for creating a proof or setting up a proof is to set up what's called a T-chart that shows the given information. So when we say T-chart, what we're talking about is something that looks exactly like that, a T. As we begin writing proofs, we will put statements on the left side. So all of the planks of our argument, if you will, and then reasons, support for those planks on the right. The given information, if we put it in here, would look like this. We're given rectangle, RECT. That's the statement. The reason that we can list it in our list is because that's what we're given. So you have the 4-step plan for writing a proof. Make sure that you're starting with a conditional. Clearly identify hypothesis and conclusion, because those things become the given information and what you have to prove. We need a labeled diagram that shows the given information, and then we set up the T-chart and list what was given. Now, as we progress later in this chapter, we'll add other statements and other reasons, but for today, this is our setup. We're going to today introduce you to writing proofs by having you do something that you'll remember from your algebra class, which is documenting why each step in the equation solving process is allowable. And we just want to remind you today, before we start that work, that there are certain properties from algebra, properties of equality, that you've used before. As you look at this guy, we start out with the idea that the equal sign belongs there, A is the same as B, then adding the same thing to both sides is allowable and retains equality. That's the addition property of equality. Here we've subtracted the same value from each side, and I'll bet you that you know it's called the subtraction property of equality. Here we're saying, okay, we're multiplying both sides by the same value, multiplication property of equality, and finally the division property of equality. So the four operations, each property's on their own. The last one's a little bit different. If you know that two values are identical, then you can use them interchangeably. That is, B can become A in any expression. Folks, that is called a substitution property, and we will use that frequently. Let's take a look at writing an algebraic proof. Here's the conditional statement, so we don't have to rewrite anything. It's already given in conditional form, that if 3 times the quantity x minus 2 is equal to 42, then the only thing x can be is 16. As we solve this equation, we're going to be, notice by the way, hypothesis is the given, what we need to prove is the conclusion. The things that are allowable to us to use as reasons are given, which we're going to use right away, properties, definitions, postulates and theorems when we get to the geometric side of things. All of those are fair game for proof writing reasons. In this proof, we're going to begin with what they gave us. So the first reason here is given. That's what they told us was true. 3 times the quantity, x minus 2 equals 42. As you look at what's next, I would ask you, what's the first thing that you would do in solving this equation? And I would bet almost every single one of you would say distribute. So I'm going to write that here. We're going to use the distribution property, or distribute is fine. The result of that distribution would be 3 times x, 3x, minus 3 times 2, so minus 6, equals 42. We only worked on one side of the equation when we distribute. As you look at the next line, what makes it different from what was on top is that 6 has been added on both sides. Folks, that's applying the addition property of equality. If you write addition prop, that's wonderful. The next line shows the result of doing this work. Depending on how detailed your proof is, some people don't show this step, add on both sides. We're going to start out just so we don't get lost. But what we've done in the fourth step is rewrite or simplify. If you write here substitution, that's okay, because what you've done is substitute a 0 for negative 6 plus 6. You could also write here, and it would be fine, simplify. Okay? I will totally understand it if I see simplify there. The next step we've given the reason, so we've got a clue here. They applied the division property. So what would we be dividing by? Yeah, you got it. We need x by itself, so we're dividing by 3. 3x divided by 3 is the same as 48 divided by 3, and that's the division property. Then the last step is going to be another simplify or substitute. I'm going to write simplify, although either word would be fine. X on the left side and 48 divided by 3 is 16, which we said that's where we have to get. So you've written an algebraic proof there, taken each step in order, given a reason for each of the steps. I'd like you to try that on this one. I'm going to ask you to pause the video. When we come back, I'll have my proof written there. Remember, we're already in conditional form, so the given information is 3x plus 5 over 2 is equal to 7, what we have to prove is that x is equal to 3. Let's set up the t-chart. Statements on the left. I'm going to abbreviate there. Reasons on the right. And we're going to fill in the given information to start with. 3x plus 5 over 2 equals 7. Alright, let's pause the video. You work this equation out step by step, and remember, you must give a reason for every statement that you make. Here is my completed proof for that equation. I started out by using the multiplication property. Multiplied both sides by 2, because doing that, the 2's cancel. I then subtracted 5 from both sides. My goal is to get x by itself. So subtraction property. Finally, to get x alone, I divided both sides by 3 and simplified. And I'm sure that your proof looks much like that. Alright, for our final activity of the day, I'd like us to focus in on a proof that has some geometric connections. It still uses the algebraic properties that we used earlier, but it's just about a geometric situation. What you can see is that if AB is equal in length to CD, and those two segments are marked in the diagram here, then it must be true that AC is equal in length to BD. And if you look at the diagram, you'll see, well, yeah, that's got to be true. You're adding the same value, the length of segment BC, to each of them, then you're going to get equal critters. That's my plan. Okay, my plan is going to use some addition, because we're going to add the same thing to both sides, and then we're going to do a little bit of geometric thinking. Okay, so the hypothesis in the conditional becomes the given information. AB is equal in length to CD. The conclusion is what we need to prove, that AC is equal in length to segment BD. And finally, we're ready to begin. Let's put that given information there. And here we go. This statement, number 2, as you look at it and how it compares with statement 1, the only thing that's different is they show that they've added the length of segment BC to both of these sides. Folks, that is the addition property that we've just talked about. If you write addition, that will be fine. The next one is a little bit more geometric. The length of AB, and that's this piece of the segment, plus the length of BC, and that's this length. That is equal, it says, to the total from A to C, and that is true. That's the segment addition postulate. Now you'll see I have an extra line here because that's part of what we have to get to. We've got the AC thing going. We got to get the BD thing going in there as well. So let's see if we can apply the same trick here. If we add from B to C to the length from C to D, we get the whole thing BD. That's another segment addition. I'm not going to write the reason again, but I am going to write the other sentence here. BC plus CD equals BD. And those are all lengths of segments. Segment addition. The sum of the parts is equal to the whole. Finally, folks, we can do some substitution. So I'm going to give you the reason. And then we're going to go back and look at how this is possible. I see this, AB plus BC, is exactly the same thing, is equal to AC. And folks, up here in this statement, we had an AB plus BC. We're going to substitute an equivalent for that. So AC. Here, we can do the same thing. That BC plus CD, that's the same thing that's written right here. So we can substitute an equivalent for that, and that would be the length of BD. And folks, that's where we had to get here. We've shown algebraically that the segment AC has to be equal in length to the segment BD, given we started with AB and CD being congruent segments. I'm going to ask you to think about this. I know this is new for some of you. We're going to talk about it a lot in class. I'll see you in school.